Now, then we're going to continue with the topic that everybody has been asking about for the last week. When are we going to do limits? So now we're going to really do limits. So now the actual calculus starts. We've got the foundations that we need to start building this stuff up. Okay, so this is 2.1. Limits. Probably take 2 lectures to do limits. OK, so what is a limit? You all have some concept of what a limit is. You have no concept of what a limit is. Help me a little bit. What is a limit? What is your concept of a limit? Sure.
It's intuitively.
Intuitively, yes.
Follow a curve from both sides.
Yep.
An x value.
Yep.
The value that the curve approaches.
The value that the curve approaches as we get close to a particular point. Sure. That's our intuitive idea of a limit, right? So if we draw a few pictures here, can you actually read this blue marker still? OK. When it starts to fade, I'm really close to it. I can see it really clearly. People in the back are going to lose sight of it long before I do, so let me know. All right, so this is an easy case, maybe. Maybe this is x naught, and maybe this is 1. Again, as we approach x naught from the left or from the right, we come along this curve, right? And we're hitting this value. So in this case, limit as x approaches x naught of f of x equals 1. This is a nice continuous function. We don't have to have continuous functions to have limits. All right, so I could do another example where there's a hole here, and maybe the value is up here. X naught. Maybe this is 1 again. Right? And it doesn't matter that the value at x naught is up here, of course. What matters is what happens as we're getting close to this value. So again, as we're getting close, we're coming to this point here. OK, now what do we want? We need a really precise way of defining limits, right? I'm confident you all have an intuitive idea of what a limit means, but when I said, can you define one for me, it's not so easy, right? So we're going to try to make this really precise. So I'm going to say, let's say we have a function. And we happen to know that the limit as x approaches x naught of f of x is equal to some value L. Okay? And what we want to know is, what does this mean? How can I look at a function and decide that this is true? So this is our goal, to try to see, what does this mean? Okay, we know the value of the function might never actually be equal to L, like in this case, right? F of x is never equal to 1 necessarily. So we can't use that as the part of the definition. We can't just look at the value of f of x naught. But we expect that we can somehow get arbitrarily close to the value of L. OK, so let's draw another picture. OK, so let's say here's x naught. Here, this looks like it's probably my L. OK, we may or may not ever reach the value of L. In this picture we do, but we don't have to. But what do we expect? We expect we can get arbitrarily close. So what I'm going to do is pick a tolerance, or you're going to give me a tolerance, any tolerance that you like, and say we should be able to get at least that close to the value of L. And your tolerance could be 0.1, or it could be 10 to the minus 100, or as small as you like, and I can get that close to the value of L. So let's pick a tolerance. OK, I'm going to call this tolerance epsilon, some positive number. OK, and what do we think? We should be able to force. What? The f of x minus L is less than epsilon in magnitude, right? But f of x is very close to L. So if f approaches this limit L, we should be able to get this inequality to happen, as long as x is sufficiently close to x naught. Yes? So let's draw my tolerance on here. Let's say that this distance is epsilon. And we'll do it again above. This distance is epsilon. So I want to be able to force f to fall within this window. Okay, and we should be able to do that as long as we stay close enough to x naught, right? If we take x out here, we're not going to fall in that window. But no matter how small I make this window, I can certainly do it. And what do we need? We need x to be within here, this window. So I'm going to look at this thing and say one of these distances is smaller than the other. I'm going to take the smaller distance and call it delta. Okay, so let's call this distance delta. Okay, so we need x in this window. So we're going to call the smaller side of it delta. Just again, some positive number. And now what do we expect? We expect that now if this point is x naught minus delta, and over here is x naught plus delta, as long as we choose x to be within this region, we should be able to guarantee that f of x is within this region, yes? Okay, so as long as x minus x naught is within this window, delta, we should be guaranteed that indeed we come as close as we want within our tolerance epsilon to this value L, to the value that we're calling our limit. We happy with the picture definition so far? Yep, okay, so this is the picture definition. Now the picture definition is not the rigorous definition. So we're going to try to write this down in really precise language. So here is going to be my definition of the limit. All right, so we say that f of x approaches the limit L as x approaches x naught if okay, and I'm just going to try to write down in words exactly what I just explained on the picture. If you give me any tolerance you like, epsilon was the tolerance, I don't care how small it is. So I'm going to say for all epsilon greater than 0, no matter how small it is, I should be able to find this window here, right? So this window is really determined by this value delta. So what I'm going to say is no matter how small epsilon is that you give me, I can find a delta. In other words, there exists some value of delta greater than 0, such that we're guaranteed that f of x minus L is less than epsilon. Right? We're guaranteed that f stays within this window here, as close to L as we decided we wanted it, whenever x stays within this window decided by delta. The one thing we're going to exclude is this point here at x equal to x naught. We do not care what happens when x equals x naught, right? Just like in this picture. So I'm going to say whenever 0 is less than absolute value of x minus x naught is less than delta. Right, and we write this part you know. We write that the limit as x approaches x naught of f of x is equal to L. Questions on this definition? We're going to do plenty of examples working with it. Take some practice to get comfortable working with it. But are we OK with the basic definition? Question?
So if we would talk about limits approaching, like as x goes to infinity,
yeah, we'll get.
require a new definition?
It requires an alteration on this definition. Yeah, we'll get there. Probably not today. Probably on Tuesday we'll get there. This definition is important. So with all the key definitions throughout the semester, you want to make sure that you know them. There's two things. You want to make sure that you know them. And sometimes on an exam, I'll ask you to write down a definition. And you want to make sure you know how to use it. Just memorizing it by rote is not going to help you be able to use it. It will probably not even help you be able to write it down correctly. So I want you to be able to write it down correctly, but I want you to be able to write it down correctly by understanding what this thing means, by being able, at least in your mind, to say this is the picture that's going on, and now let's write this down in words. Okay? But again, you need to know the definitions. They're important in this topic. Okay, so let's do some examples. Okay, so let's start. Simple. F of x equals c times x is a linear function. Okay, and we want to show that the limit as x approaches x naught of f of x is equal to c times x naught. Okay, and we want to show it using the definition of the limit. So in all of these problems, I'm going to tell you right away what is the first step that you're going to do in all of these problems. Your first step is going to be to say, let's choose any epsilon bigger than 0. Okay, now we know, again, we have with a lot of these proofs and exercises, we have a goal. Our goal is to try to force this to happen. Force f of x minus L, which is cx naught in this case, to be less than epsilon. So we know this is our goal. We want to force f of x minus cx naught to be less than epsilon. Okay, so we're going to start by writing down what this is, right? We know what f of x is. So f of x minus cx naught is cx minus cx naught, right? We substitute in the information that we know, and we try to simplify. We know as we're trying to simplify, we're trying to come up with some requirements on x minus x naught. So as you're simplifying, you should have that in your head. I'm looking for terms that look like x minus x naught because I want to put some requirements on this. So in this case, I can do it by factoring out the c. I'm going to pull out the absolute value of c times the absolute value of x minus x naught. Okay, and I know that we want this to be less than epsilon. So we need to write down the condition that will make this true. Well, what is the condition that will make this true? This is true if, and now we can solve for this x minus x naught. So if x minus x naught is less than epsilon divided by absolute value of c. So we wanted a condition that said this works as long as x minus x naught is less than delta. This plays the role of our delta now. We said x minus x naught is less than this term, so this is going to be our delta. Okay, and that's the whole calculation. That's the whole proof that this works. We've said no matter how small epsilon is, I can always find a value of delta, right? As epsilon gets smaller, as my window for f gets smaller, my window for x will get smaller. But I have a window. I always have this window that will ensure that I can make f of x minus L less than epsilon. Okay, so this satisfies the definition. Okay, so we can conclude that indeed the limit of f of x as x goes to x naught is equal to c x naught. Questions on this example? Okay, this example was simple in some ways, in many ways, because it's a linear function here. But even though it was simple, we can hopefully pull a basic strategy out of this. It will always be our strategy. The details will sometimes be more complicated, but let's try to write down our basic strategy here. Yes?
Do you have to say something like for c not equal to 0?
For c not equal to 0, sure. In fact, what's really going to happen if c is equal to 0, f of x is the 0 function, and f of x minus 0 will be less than epsilon for all values of delta. So in some sense, this thing goes up to infinity, and you can actually take delta whatever you like, right? Because f of x, no matter how far apart your x values are, f of x is still 0. But yeah, to be precise, c should be 0 there. Or c should be not 0 there. Okay, so here is our strategy. Okay, so we choose an epsilon bigger than 0. That's always our first step. And then what did I do? I wrote down f of x minus L here. Okay, and then we simplified. And our goal in the simplification was to get some term that looked like this, that looked like x minus x naught. Okay, so simplify. Simplify is where most of the work is going to be done typically. Simplify was easy here because it's a linear function. It will not always be that easy. So simplify with the goal, not just blindly, but with the goal of extracting a factor of x minus x naught. Okay, once you have some constant times x minus x naught, some stuff that you can control times x minus x naught, then the hard work is typically done. Now we say let's make this be less than epsilon. So require to be less than epsilon. That was this line, right? And that gave us a way of solving for our condition on x minus x naught, or our condition on delta. So we solve for a condition on x minus x naught to obtain our delta. Yes?
So in this example, the way the logic flows almost implies that given if we assume f of x minus cx naught is less than epsilon, we can show that there's a delta. But it also reads that if there's the delta, it shows the other one.
Right.
It seems
So
to be a bidirectional implication.
this is an equivalence.
Yeah.
Exactly.
Is that always going to hold? Because we only need to show the implication from delta implies the epsilon.
Right. So it's typically easier to show it this way, is to start by saying, okay, if this is less than epsilon, what would have to be true of my delta? So that's almost always going to be your easiest way to do things, right? So at this point I said, you can even, sometimes I write this as a question mark. Can I make this true? And the answer is yes, I can make this true as long as I choose my x minus x naught appropriately.
But there may exist limits where, like, you can't, it may not be equivalence, right? Like, you may have to, like, make an assumption or something.
We'll have to add extra assumptions along the way sometimes. Again, this is simplify step was one line here. It's not always going to be one line. We're going to have to sometimes bring in some extra assumptions along the way and make sure that we can validate them. And typically, the extra assumption along the way would be we need delta to be small enough for this to work. So a lot of times you'll start by saying, let's just pick delta to be less than 1. Okay, maybe my window allowed delta to be equal to 2, but delta equals 1. By forcing it to be smaller, it will still keep f in this range. It might keep it tighter in the range. So there will be extra assumptions that are going to come in the next few minutes, probably.
And we can always make delta the smallest we want as long as we stay, right?
You can always make delta as small as you want as long as it's positive.
Yeah.
Yeah, as long as you maintain this is less than epsilon. It doesn't have to be that this is tight, that this is as close to epsilon as possible. Maybe this ends up, the delta we pick ends up making this less than epsilon over 100. That's fine. It's less than epsilon over 100, it's still less than epsilon. And we'll do that sometimes. We just need bounds. All right, so let's do some more examples. Try to build these up to be sort of gradually more complicated. All right, so my next example is, this is going to be a piecemeal definition of this function. So 2x squared minus 3x plus 1 over x minus 1. And this is a valid definition as long as x is not 1. And I'm going to let this be equal to 5 if x is equal to 1. And we want to show that this limit, so that the limit as x approaches 1 of f of x is equal to 1 in this case. Okay, so in this case, we're not expecting the limit to be equal to the function value. And yeah, that's OK. That's valid. OK, so we have a process. We're going to try to follow the same process here. So we know line 1. Line 1 is always start with an epsilon. OK, then line 2 is always to write down the absolute value of f of x minus L. And we want to do this for values of x that are close to 1 in some sense, but not equal to 1. Again, we do not care what f does exactly at the value 1. We just care what happens nearby. So what I'm going to say is, for x not equal to 1, because that's going to make it a lot easier to write down this function, f of x minus my limit, which was 1. OK, so since x is not equal to 1, I can ignore this little piecemeal bit here and just use this definition. OK, so this is going to be equal to 2x squared minus 3x plus 1 over x minus 1 minus 1. OK, next step is simplify. Okay, obviously, it's a little bit more work here than it was in the last problem because this is not just linear. But this is something that you know how to simplify. Right? I mean, you've done limits of this kind of function in Calculus 1. The same techniques you use to evaluate the limits are going to be the kind of techniques you use to do your simplification here. So factoring, of course, is one of your big tricks. Okay, so if I factor this, what do I get? 2x minus 1, x minus 1 over x minus 1 minus 1. OK, x is not equal to 1. We've started with that assumption. X is not equal to 1. So there's no problem having this x minus 1 in the denominator. There's no problem canceling these two factors, right? It's not a 0 over 0 thing that I'm trying to cancel. It's something small divided by something that's small but the same. So it's perfectly valid for me to cancel those. OK, and this is looking like 2x minus 2. If I factor out the 2, I get 2 times x minus 1. And this is good. This is what we want. So step 3 or whatever it was, I don't know, was to simplify.
Absolute value around 2?
Shouldn't there be an absolute value around 2? Well, 2 is already positive. It doesn't matter. Right? So if I had a minus 2 times it, then I would have to make it a positive. But. OK, so I've got it simplified. And I've got it simplified to the point where I can see clearly this factor of x minus x naught. Right? My x naught was 1 here. That's what this is. So this is the step where I say, can I make this less than epsilon, and how do I do it? So if I want to make this less than epsilon, say, sure, this works as long as x minus 1 in magnitude is less than epsilon over 2, which becomes my delta. Okay? And again, that's it. That's the whole rigorous argument that indeed the limit as x approaches 1 of f of x is equal to 1. Questions? OK, this was the next simplest thing. It was not a linear function, but it's almost a linear function, right? Because in some sense, this thing here, well, it sort of looks like a rational function. But really, when I factor it out and cancel things, I've got another linear function, right? So again, simplification is not so hard here. So now, the next obvious step is we need to see if we can make this definition work for things that are really kind of genuinely and intrinsically nonlinear near the point x naught. This is nonlinear, but it's sort of linear in a deleted neighborhood of x naught. Okay, so let's do something that's actually very nonlinear. Let's do something quadratic to start with. And we want to show that the limit as x approaches 3 of f of x is equal to 21. OK, our process doesn't change. We need our epsilon. OK, so we got our epsilon. Then we need to write down our f of x minus L. So that's f of x minus 21. OK, so if we write that down, what do we get? X squared plus 2x plus 6 minus 21. That's minus 15. OK, again, we have tricks for simplifying this. We can factor it. So if we factor it, what happens? We get an x minus 3 times x plus 5. And this is now looking partially good and partially puzzling. Right? So when we did the simplifications before, I would get something like, here's my x minus x naught. This is good. So this is x minus x naught. But before, when I did this, I would get something like a c or a 2 or something constant out here. Now I've got something that's non-constant out here. So it's not immediately obvious how I'm going to just pick a delta that's just a number that doesn't depend on x. So what we need to do, we need to try to control this factor. So we need to try to bound this term. When x is, I'm going to say, close to the value of 3. Okay, so this is where I start by saying maybe delta equals 2 is fine. But if delta equals 2 keeps my function under control, a smaller window will also keep my function under control. So I'm going to say, let's just assume delta is less than 1. Right? It might end up that we need to delta a much less than 1. Maybe delta equals 1 is actually bigger than what we wanted or what we needed, but delta less than 1 is safe. So this is going to be your general approach when you have these non-constant terms that you have to control, is to say, let's assume delta is small, and let's give it a value. So let's restrict our attention to delta less than 1. Okay, I don't have to pick 1. I could have picked delta less than 10 or delta less than 0.03 or whatever, but 1 is convenient here. So what do I know? We want x minus 3 to be less than delta. Which is going to be less than 1. We're going to require it to be less than 1. So let's play with that a little bit. That means that minus 1 is less than x minus 3 is less than 1. All right, now this is not the thing that I'm trying to control at the moment. We need restrictions on this eventually. The thing I'm trying to control at the moment is what happens to x plus 5. Okay, so what I'm going to do to try to get a handle on x plus 5 is I'm just going to add 8 to all the way through this inequality. So if I add 8 all the way through this inequality, what do I get? 7 is less than x plus 5 is less than 9. So if we know x naught is equal to 3, we know that we're within a window, within a radius 1 of that point. Okay, x could take on lots of different values. We're not sure what it is, but we know it's stuck in this window. And in particular, we know that the absolute value of x plus 5 is never going to get bigger than 9. Right? It might end up being less than 9. It might end up being a lot less than 9. But it's certainly not bigger than 9. Okay, so this is a little interlude in our simplification step. Now I'm going back to the thing that I want. The thing that I want is to control f of x minus 21. I need to make this less than epsilon. So let's go back to f of x minus 21, which we said was equal to x minus 3 times x plus 5. And now I happen to know that as long as we stay within our window, this term is going to be less than 9. So this is less than 9 times x minus 3. Right? This guy was my x minus x naught. And I know I'm trying to force this whole thing to be less than epsilon. Okay? And this is where things are not tight, right? This less than is a question mark, right? And what we really need is this less than epsilon. We've put some interludes in the middle, and that's safe, but it means that it may end up being a lot less than epsilon, not sort of arbitrarily close. And that's OK, as long as we can get it small. So this will be true if, and now we have a way of solving for our x minus 3, our x minus x naught, if x minus 3 is less than epsilon over 9. So what is my delta here? You think it's epsilon over 9? It's a trick question. It also has to be less than 1. If you have, it's a minimum, exactly. If you happen to give me epsilon equals 10, this argument wouldn't have worked, right? So if we take delta to be equal to the minimum of these two things, right? So we made a couple requirements on delta. Here, we have a requirement that delta is less than epsilon over 9. Or less than or equal to epsilon over 9. Here we had a requirement that delta better not be bigger than 1. So we should take delta be equal to, or to be less than, the minimum of 1 and epsilon over 9. Right? And in more complicated problems, you may bring in more requirements along the way, more assumptions that you need to try to control things. And again, then you'd say at the end of the day, that's fine, I brought in all these assumptions on delta. I just need to make sure at the end of the day that I take delta to be less than all of those things that I assumed about it. So you'd stack them in this minimum. Okay, and then what happens? Then if x minus x naught was 3 here, is less than this delta, we're guaranteed that f of x minus 21 is less than our epsilon. Okay, and again, once we've found our delta, we've identified our delta, then we're done. Then we can say, great, we've satisfied the definition of the limit. The limit as x approaches 3 of f of x is equal to 21. Questions here? Okay. So it's the same process that we wrote down before. The simplification step got a lot longer this time than it did in our first example. But again, we're always moving with a goal of trying to extract this factor of x minus 3. And then along the way, we need to keep simplifying, so we need to try to find bounds on what are less. Yeah?
You assume that delta was less than 1.
Yes.
The minimum is 1.
Yeah.
That means delta is 1.
Delta might be 1, yeah. So if we happened to say, you're not very conservative on your tolerance, and you just say, I want to get within epsilon equals 10 of this value, right? Then I'd say, OK, to get within epsilon equals 10, well, this is bigger than 1, so I'll just take delta equals 1, and that's good enough.
It doesn't matter that we assume that it was strictly less than 1?
It doesn't particularly matter, because actually I could say, I could do this all the way through, and it wouldn't actually change anything. But it is good to worry about those things, because sometimes this matters. Yep.
Is there a good trick for keeping track of which logical statements are assumptions and which ones are true?
Which ones are assumptions and which ones are true?
I could draw question marks, I guess. But
So I do that sometimes. I'll draw question marks, and I'll say, OK, this, under the assumptions I've made, these are all true. And now, can I make this true? The reason that I'm safe not doing it is because I immediately followed by the line, this is less than epsilon if I force this to be true, right? So I had an immediate condition that made it true.
okay.
Um,
I guess you could think of it as like a leftward-facing implication.
Sure, yeah. OK, so let's try some more nonlinear things. Again, these problems are tricky the first time that you try to do them on your own. By the end of the semester, you'll wonder why you ever thought they were hard. This is my hope and my goal. But the big thing is just to do lots of these problems, and they get easier. OK, let's show that the limit as x approaches 0 of 2x cubed minus x squared is equal to 0. OK, so we start the way we always start. We pick an epsilon. And we write down our f of x minus L. L is 0 in this case. OK, so this is 2x cubed minus x squared. And I'm going to, again, we're on the simplification step. Factoring is always a good tool when we're simplifying. So I can certainly pull out an x squared. X squared times 2x minus 1. Okay, this term is a good term, right? This is my x minus x naught. It's my x minus x naught squared, but that's okay, right? It's a factor that involves my x minus x naught. This term is the one that we need to try to control. So we're going to need to control near x equals 0. Okay, I'm going to do the same thing that I did before and say, right, I don't care what happens really when x is equal to 1,000 or anything like that. I care what happens as x gets close to 0. So let's focus in on that area. Let's restrict our attention to delta being no bigger than 1. And again, we'll probably end up taking delta less than this if you've given me a reasonably small epsilon. But we can build that in, just like we did here, into the minimum. Okay, so what do we know? We know that x is going to be less than delta, which is less than or equal to 1. So minus 1 is less than x is less than 1. Or minus 2 is less than 2x is less than 2. I'm trying to get at 2x minus 1. So I'm going to subtract 1 all the way through here. So I'm going to get minus 3 is less than 2x minus 1 is less than 1. Okay, and that gives me the information that I need, right? I'm trying to control 2x minus 1. I'm trying to control its absolute value. Now we know here that its absolute value is never going to get bigger than 3. Okay, so absolute value of 2x minus 1 is certainly less than 3, as long as we stay within this window, within a distance 1 of x naught. Okay, so that's most of our simplification work. Again, we're going to go back to the thing we cared about. The thing we cared about was f of x minus L. So if we go back to f of x minus 0, which we knew is equal to x squared times 2x minus 1. And now we can say, well, this term is certainly less than 3. It might be a lot less than 3, maybe just a little less than 3. But it's not bigger than 3. Okay, so we've simplified things. This is a constant. This is a factor that involves our x minus x naught, squared in this case, but that's okay. And we want this to be less than epsilon. Okay, and again, we can do that. This works if x squared is less than epsilon over 3, or equivalently, absolute value of x is less than the square root of epsilon over 3. Okay, so again, now we're in business to write down our delta. We've found conditions that will ensure that f of x is less than epsilon. We have two conditions. One was that delta shouldn't be bigger than 1. One was that delta shouldn't be bigger than root epsilon over 3. So if we take delta equal the minimum of 1 and root epsilon over 3, then we can satisfy the definition. Okay, and this is fine. This delta can involve nonlinear functions of epsilon. In our first couple examples, it was always like epsilon times a constant, but it doesn't have to be. It just has to be some constraint on our epsilon, or some constraint on our delta. We happy with this example? Yes? Okay. Let's go a little more nonlinear then. So let's try to show that the limit as x goes to 0 of x times sine 1 over x is equal to 0. Okay, this function is not defined at x equals 0, right? Because if I plug x equals 0 into here, I get something that makes no sense, right? This is not defined at x equals 0, but it's defined arbitrarily close to x equals 0. So we at least have some hope that we can ask about a limit. Because I can put in x very small and positive. I can put in x very small but negative. And those are both allowed. So just note that. F of x is not defined at x equals 0. But that's OK. We don't need it to be defined there in order to have a value of the limit. OK, so we know the first step. We write down we pick our epsilon. Let's choose our epsilon. And we know when we're doing all these manipulations, we're going to be assuming hopefully that x is close to 0, but x is not equal to 0. Because again, if x is equal to 0, this makes no sense. OK, so as long as x is not equal to 0, what do we have? We have that f of x minus L, that's f of x minus 0, is equal to x sine of 1 over x. All right, so how's my simplification step going to work out here? I can bound it. Yeah, how can I bound it? We know that the sine function is going to be oscillating like crazy. I have no idea what value it's going to take on. But it's never going to get bigger than 1 in magnitude. Exactly. So we know that this is less than or equal to the absolute value of x, since the sine function is never going to exceed 1. OK, and with that observation, this becomes a really simple problem to finish, right? I want this to be less than epsilon. And this is true as long as I take x to be less than epsilon. So here we take delta equals epsilon. Okay, so this is your general approach always, right? It's not always this easy to bound a nonlinear function, but just like we did for our quadratic and for our cubic functions, we're trying to find bounds on what's happening nearby and try to somehow get out a factor of our x minus x naught. All right, you happy with these problems that you can sort of prove some of these limits using the definition yourself? OK, then let's do a slightly different example. Turn this on its head a little bit. OK, almost the same function, but I'm going to leave out the factor of x at the beginning. What's this limit equal to? It doesn't exist, right? This thing, as x goes to 0, this 1 over x term is going to get bigger and bigger and bigger and bigger, and the sine function is just going to start oscillating infinitely quickly. So this, we expect, does not exist. All right, the picture of this function is going to be that we have sort of gentle sine waves that are going to get faster and faster and faster and faster. And you're going to have things moving, oscillating infinitely quickly here and never approaching any limit. OK, now we have a definition of a limit. This is our intuition. Our intuition is what happens to the function when we get close to 0, close to x0. But we know we have a rigorous, precise definition that tells us if a function has a limit, and how can we verify that. So this is turning things on its head. How do we show that a function doesn't have a limit? How do we show that the limit does not exist? So we need to try to write down that definition and then write down the opposite of that definition and see if we can verify the opposite of that definition. Okay, so to hand wave, so let's recall the definition of the limit. Let's not hand wave first of all. Let's write things down precisely. Okay, so the definition of the limit, f of x approaches L as x approaches x0 if for every epsilon greater than 0 there exists a delta such that if x0 is in the right window, then f of x is in the right window. Now, if we're going to turn this on our head and say we can't make this definition be satisfied, so can we negate this? Negating it means, right, the definition says for every epsilon greater than 0, we can do this. Now, if there's not a limit, if this definition doesn't hold, that means somewhere out there, there's a value of epsilon for which we simply cannot pull this off. We cannot find a delta. So negating it says somewhere out there, we found an epsilon for which this definition fails. So this would say there exists a an epsilon greater than 0 for which this definition fails. In other words, I cannot find a delta that will force this to be true, that will force f to stay in the window that I want. You take delta as small as you want. Take delta to be 10 to the minus a googolplex or something like that, which is really, really small. It still won't be good enough, right? I still cannot force f to stay in this correct window. This says there exists some epsilon for which this fails, for which no matter what delta I pick, no matter how small it is, I can't force this to be true. We can find some value of x that gets this bigger than epsilon. So we can find some x satisfying, so in our teeny tiny itty bitty little window, so satisfying this inequality that it's less than delta, satisfying this, and even though the x value is in this teeny tiny itty bitty little window, the f of x value still escapes. So f of x minus L is bigger than or equal to epsilon. Okay, if we can do this, then we'd show then the limit as x approaches x0 of f of x does not exist. Yes?
This would hold for some real number L, right?
So this would hold, and this would be true no matter what L is, yes. So we can also put that at the front. No matter what value of the limit you try to pick, you cannot pull this off. Okay, so in this example, for example, I could pick epsilon equal a half, say, right? No matter what value of L I pick, this thing is going to oscillate away from that. So if we choose epsilon equal to a half, a quarter, let's make it a quarter, should be a little bit safer. Right? No matter how small delta is, with x in this window, in the teeny tiny itty bitty little window, the function f of x, even in this teeny tiny little bitty window, is going to take on all the values between plus or minus 1. We agree with this? Okay, and that means no matter where I try to set my L, I might try to set my L here. In this little bitty window, the function is going to oscillate away from that L, and it's going to get farther than a distance a quarter, say, away from that L. No matter where I choose L, the function will, at some point, satisfy f of x minus L is certainly bigger than or equal to a quarter, which was my epsilon. Right? Because this thing is taking a swing of plus or minus 1 in each direction. It's not going to stay within a distance a quarter of anything. Okay, so here there is in fact no limit. Okay, I'm going to do another example of a limit failing because I think it's a little harder to think through these. But here, right, notice the difference. When we were satisfying the definition of the limit, we wanted to show that for all epsilon this works. If we're going to violate this, we just need one counterexample, essentially. We just need to pick one particular value of delta that makes the definition fail. And if one value of epsilon makes the definition fail, the definition fails. Okay? So, for example, here I could just say, for epsilon equals a quarter, this definition breaks down. And that means the whole thing breaks down. I don't need to check any other values. Okay, so let's do another function that also does not have a limit. So I'm going to define this to be minus x squared when x is less than 0, and x squared plus 1 when x is bigger than or equal to 0. Okay, we're going to try to do this one carefully and precisely. This is a nice example to write down. This one, because it's a little simpler function, it will be a little easier for us to very carefully and precisely write everything down. Okay, so if I draw this function, what does it look like? If x is less than 0, it's going to be minus x squared. And if x is bigger than or equal to 0, I'm going to take the positive of x squared and shift it up. Okay, and we're going to be interested in, of course, the limit as x goes to 0, because that we know, we have intuition that tells us that limit shouldn't exist. Intuition is great when you're doing simple quadratic functions or piecewise quadratic in one dimension. Of course, when you go out into the real world, things are more complicated and your intuition won't always work. So we need to be able to do this precisely, but we want to show that the limit as x approaches 0 of f of x does not exist. Okay, so I'm going to start by saying, let's suppose the limit does exist. Suppose we have some value of the limit, and we're going to call it L. We're not sure what that value is yet. And I'm going to try to show that no matter what L is, this definition breaks. No matter what L is, I can find some epsilon that makes this thing fall apart. Okay, so let's suppose there is a value of the limit. Okay, this is 0, this is 1. Now I just need to find one value of epsilon that will make this definition break. What would you propose is a good value of epsilon? Well, we've got a gap here, right? We know that we're trying to keep f of x minus the value of the limit within some distance epsilon. What's a value that we're not going to be able to pull off? 1/2, yeah, half the size of the gap. So half the size of your gap, or something smaller than half the size of your gap, is usually a good choice of your epsilon to try to break this definition. Okay, so we need to construct a value of epsilon that, let's say, breaks the definition. Okay, and since we happen to know that we expect to see this jump of distance of 1, then taking something that's half that jump is a reasonable starting point. So let's try taking epsilon equal to 1/2. Okay, so if this limit really exists, then there's some value of delta that should keep f within the window I want, yes? So we're going to focus on x in this window. So 0 less than x less than delta. Where delta is whatever value we needed to make this limit work. Okay, so I'm going to take two possibilities. I'm not sure what L is, so, and this is, again, a strategy you can always use in your proofs, is you can break things down into cases. So the obvious place to break things down is L somewhere up here, or is L somewhere down here? So I'm going to break this into, is L bigger than 1/2, or is L less than 1/2? So case 1. L is less than or equal to 1/2, right? All I've assumed right now is there's some limit, and I don't know what it is. So what I'm going to try to do is exclude all possible values of the limit. Say that actually none of them work. They all make the definition break. Okay, then what can we do? Then we can find x. Let me say this. Then we can take, say, x equal to. So what we want to do, our limit, this is 1/2. We've assumed our limit is somewhere down here. We're trying to find a value of x where f doesn't get close to that. So we should be trying to take a value of x over here that's positive, right? It's positive, and it has to live in this window. So let's take x equals, say, delta over 2. Okay? And then indeed we do have that 0 is less than absolute value of x is less than delta. Right? So our x values are within the required window. That means our f values should also be within the required window if the limit happens to be less than a half. Okay, so what do we know about this particular value of f? F of x is delta over 2 squared plus 1 in this case. And let's just simplify things down. This is certainly bigger than 1, yes? Okay, and that means that f of x minus L f of x is bigger than 1. L is less than or equal to a half, right? So this term is bigger than this term, right? So I can write this as f of x minus L. I can drop the absolute values. Okay, this guy is bigger than 1. This guy is less than a half. So we know that this distance is bigger than or equal to, it's bigger than a half, which was my epsilon. Right, and this is breaking the definition, right? We've said if the limit is less than a half, if there truly is a limit and it's less than a half, then for this value of epsilon, I should be able to find a delta that makes f of x minus L less than epsilon, okay? But no matter what delta is, actually it doesn't work, right? No matter what delta is, I can make f of x minus L actually bigger than epsilon. So this doesn't work. We must have that L less than or equal to a half cannot be true. Okay, then we're going to do the same thing and try to rule out L bigger than a half. Right? If there's a limit out there, it's either less than or equal to a half or it's bigger than a half, and those are the only possibilities. So case number 2 is L bigger than a half. I'm going to do exactly the same thing. Okay, I erased the picture. L was somewhere bigger than here. That means I should try to take x out to the left here. So we're going to take x as the negative, right? Which again satisfies. It's in the appropriate x window. Why is x negative? I'm choosing x to be negative. So if I bring this picture back. Right? We're assuming the value of the limit now is somewhere up here. We're trying to find right? We're allowed to look at any values of x that satisfy this. We're allowed to look at any values of x within this window delta. But what I want to do is try to find one that's far away from the value of my limit L, right? That's our goal, to break things. So if L is up here, I should try to find a value of x where f is down here. Okay? And that's why I'm going to pick x to be negative. So that I'm guaranteed that f is down here, far away from the value of my limit. Okay, so this is a choice. It's a choice that we're allowed to make because we're allowed to take anything in this window. Okay, then f of x is equal to, minus x squared here, so minus delta squared over 4, which is certainly less than 0. Okay, and again, I'm going to look at this difference, f of x minus L. Okay, this time L is positive and f is negative, so I need to switch the order of things if I want to drop the absolute value sign. again, this time using the fact that L is positive, I'm going to get that this is bigger than a half. And then this is going to make it actually even bigger than a half. And again, this is my epsilon. Right? Again, we're violating the definition of the limit, right? If indeed we had a limit that was bigger than a half, then no matter what value of epsilon I picked, for example, epsilon equal a half, I need to be able to find a delta such that as long as I keep x in this window, f of x minus L is less than epsilon. But now we've seen it doesn't matter what delta you give me, right? There was nothing here that said how big or small delta was. It could be as small as you like. And no matter how small it is that you give it to me, no matter how teeny tiny this window is, we're always able to construct a value of x where f of x minus L is bigger than epsilon. F of x escapes from this window that we wanted. So again, we say the definition of the limit doesn't hold for this value of L. So that means L bigger than a half cannot be true. Right? So we've said, let's suppose this function has a limit. Well, we said there's a couple cases, but we managed to rule out L less than or equal to half. We've managed to rule out that the value of the limit is bigger than a half. There's nothing left for us here, right? So we're going to say, hey, actually, there's no value of L will satisfy the definition of the limit. Okay, in other words, there is no limit. Right? So we're going to say, in fact, now we've verified rigorously that the limit as x approaches 0 of f of x does not exist. Questions here? Yes.
So I just wanted to know real quick, how come in case 1 you made it greater than 1, but in case 2 you made it less than 0?
How come in case 1 I made it bigger than 1? So remember, I'm allowed to pick anything in this window, right? So what I'm trying to do, I'm trying to show that I can break the definition. So since L was less than a half, I knew that in case 1, the value of L is down here somewhere. Right? I'm trying to break the definition. I'm trying to show that I can get far away from L. Right? So I'm picking, since I'm not sure exactly where L sits, I'm going to pick a value of x that ensures that I'm going to escape from that area. Okay? So picking x bigger than 0 ensures that no matter where L lives down here, f of x is going to get far away from that. So that's what I was trying to do. My goal here was let's break the definition. Let's get as far away from L as we can get.